Hi guys, good morning. Hi guys there. Hello, guys.
Morning.
Yeah. So yeah, we'll quickly start. We'll quickly complete this chapter, right? Okay. So we were at the end of the chapter. I said that we'll be speaking about defects in solids, right? So that's the topic today. Okay. Fine. What I can tell is defects are basically going to come if, like, for example, we'll mostly speaking only about ionic compounds here, right? So because we're talking about crystalline solids, we already know that we have two types of solids, crystalline and amorphous, but in our syllabus we have only crystalline solids. So we are going to see defects only in ionic crystals. Okay, we are going to see defects only in ionic crystals, right? So how and all can defects come, right? How and all can defects come? So it is like I would say that say for example, if there is one ion, right, it has to be there in its position, right, and it is not there in its position, right. No, it is not there in its position, in its own position, again can be of two types, right. Say it is not even there, right, that is one possibility. It is not even there inside the crystal lattice, or it should be in a place, it is not in that place but it is in some other place, right. Hope you get what I'm saying, right. Say there is an ion, right, there can be two possibilities, like it might not be there, it might not be there in a sense, it will not, it is not there at all, right, it is not there in the crystal lattice at all, or right, it is going to be there in a position which is not supposed to be there, right, which is like there, it should not be there, but still that particular ion is there, right. So these are all the, so again there are still more possibilities than this where I can have defects in solids, right. Okay, broadly, right, broadly I will be able to classify your what is that, defects in solids into two types, right. So first one, what are called as stoichiometric defects, and the other one is what is called as your non-stoichiometric defects, right. So what do you mean by stoichiometric defects and non-stoichiometric defects? So the thing is, like we have studied what is that, laws of chemical combinations, right. So in that, one of the laws is your law of constant proportions, isn't it? So what does law of constant proportion says? If a compound is formed, right, if a compound is formed from its elements, the elements combine in constant ratios, right, ratios of masses or ratios of number of atoms or number of molecules, that ratio is going to be constant, right. So that is basically what we call it as stoichiometric ratios, isn't it, right. So for example, in NaCl, right, I require one Na plus and one Cl minus, so the ratio is 1:1 there, right. So due to these defects, right, whenever a defect is going to come, and if it doesn't affect the stoichiometry, right, and if it doesn't affect the stoichiometry, doesn't affect the ratios, the overall ratio is still constant even though the defect is there, right. So those are what are called as your stoichiometric defects. Again I repeat, the overall stoichiometry is not affected, still the ratio is constant, right, it is not changing. Those kind of defects come under stoichiometric defects. And obviously non-stoichiometric defects, obviously the ratio is going to get affected, right. Okay. So we'll see what all is happening, right. Say under stoichiometric defects I have one second. Okay, under stoichiometric defects I have Schotsky defect, Frenkel defect, and under non-stoichiometric I have, okay, fine, cool. So under stoichiometric defect I have Schotsky defect, and I have one more called as Frenkel defect. And under non-stoichiometric, I have two more: metal excess and metal deficiency. Right. So these are the four types of defects we are going to study under stoichiometric 2 and non-stoichiometric 2. Right. Okay. So we'll see one by one. See what happens. We'll start with stoichiometric. We'll start with Schottky defect. Okay. Right. So moving on with your Schottky defect. Right. Fine. So let me assume a crystal lattice like this. Say I have a crystal lattice. Right. So in this, say I have an ionic compound. Right. So obviously ionic compounds will be arranged as if like I have a positive, negative, positive, negative, positive, negative. That is how it will be arranged, isn't it? Say I'll write it like this: A plus, B minus, A plus, B minus, B minus, A plus, B minus, A plus. Say one more row. Say A plus, B minus, A plus, B minus. You can see alternatively I have arranged my cations and anions, isn't it? Right? Alternatively, I have arranged the cations and the anions. Okay. So this is my perfect lattice. There is no defect here. Okay. So in Schottky defect, what will happen is the reasons might be so many. Like reasons can be so many reasons. Say for example, it is the temperature is high. Like you supply some temperature, right? Or I can say that if you see that the size of the cation and if the size of the anion are not comparable, right? If the size of the cation and if the size of the anion is not comparable, right? So at those things at those conditions you'll be seeing the Schottky defect, right? Fine. So we'll see what exactly is this. The reason behind why Schottky defect happens is not important, but what the Schottky defect is what is important. Okay. So fine. So what happens is like I'll just put the sounds also. Okay. Fine. So what is going to happen is, say due to some reasons, right? Due to some reasons, assume that one of the A plus has gone out of the lattice, right? To for some reasons, one of the A plus ions among this is going out of the lattice. Okay. So what I'm going to do, I'm going to make sure that this A plus is gone. Okay. I'm going to make sure, I'm going to make sure something happens that one of the A plus ion is going out of the lattice. Okay. Now, I told you these comes under stoichiometric defects, right? So if one of the cation is lost, right, that means one of the anion should be lost, isn't it? One of the anion should be lost. Definitely. Why? Because I need to make the ratios constant. If one of them is gone, if one of the cations are gone, and if the anion is not going, the ratio will get affected. Now you can see the ratio is 1:1, right? For one anion, I have one cation, right? So if one cation goes out of the lattice, it has to be made sure that one anion also goes out of the lattice. So say I can remove any one of the anion. I can remove this anion, right? So this is what is called as your Schottky defect, right? So in Schottky effect, what happens? One of the cations will go go outside the lattice, and to maintain the stoichiometric ratio, one of the anion also goes out, right? So yeah, that is what is about your Schottky defect, right? So in examples, like which and all can have Schottky defect, KCl, AgBr, all these are the examples generally, right? AgBr crystals, KCl crystals will generally have Schottky defect, right? So I can understand how is it like it's yeah. So it definitely that you can see that the size of the cation and size of the anion is not going to be similar. Like they have large difference in size, and that's the reason why it happens. Okay, fine. So that's about Schottky defect. Okay. So now we'll move on to Frenkel defect. Hope everybody understood. Can I rub this part, people? Right. I think there is nothing to take down, only the diagrams, the understanding. Examples are a little important. They can ask, say, KCl will show what kind of defect, AgBr will show what kind of defect. Sometimes questions can come from that also. So make sure that you know the examples for each and every defect. Okay. Cool. Next, I go for Frenkel defect. Right. So in Frenkel defect, what is going to happen? We will see. Right. So in Frenkel defect, again I write the A plus B minus A plus B minus B minus A plus B minus A plus A plus B minus A plus B minus. Okay, now this is the lattice, perfect lattice. There is no there is no defect. Okay, so now last time what you saw happened is the A plus went completely out of the lattice, right? And in order to maintain the stoichiometry, one of the B minus also left out of the lattice, right? So here in Frenkel defect, I am going to still maintain the stoichiometry, that is the ratios are constant, but the only difference between Schottky and Frenkel is that in Frenkel, the cation or the anion is not going to move out of the lattice, right? It is not going to move out of the lattice. It is going to stay inside the lattice, but, right? Say now here, if I mark all these circles, right? These circles, I can say that these are my lattice points, right? That means what? Lattice points are the points are the only positions where the anions or cations can be present, isn't it? We already know what are lattice points. In those points only, the cations or anions can be present. Correct, right? So what I'm telling is, one of the cation is displaced, I would say, right? One of the cation is going to get displaced, right? That means it is not exactly moving out of the lattice, right? But it is not there where it should be. That means it is not there in its own lattice point. It is something. It is there somewhere else in the lattice, right? So where it will be, we can see. Say for example, I need to make a bigger diagram, but still I can explain you. Say one of the A plus is not here. It should be here, but it is not here. Okay, one of the A plus ions is not here, but where it will be is it is going to be there in the voids. It is going to be there at the voids. Say I can say that this is what I can use a different color. It might be helpful, right? Say I have the A plus ion to be here. Right, see you see that it is not there exactly in the lattice point. It is somewhere in the void, the empty spaces in the lattice, right? So this is it. Now again, you see that nothing is lost, right? You see that nothing is lost, right? So definitely this maintains stoichiometry. The ratios are still constant, but except that wherever it should be, it is not there. It is there in the voids. The cation are there in the voids, right? So this is what is called as your Frenkel defect. Right. Now the common question can be, right? Say, sir, why is the anions are not doing this? How will you answer this, people? Right? Why anions are not occupying the voids? Hello.
Not sure, sir.
Guesses? Any guesses?
Because it is very large in size.
As simple as that, right? So obviously, I know generally cations are smaller, anions are larger, right? In any compound for that matter, mostly, right? Cations are small, anions are large. So definitely, in order for it to occupy the void, anions is not possible. Only cations are smaller enough to occupy the voids, right? Okay, and one more thing I forgot to say. When I went for your Schottky defect, right? When I went for your Schottky defect, you see that one A plus and one B minus are entirely leaving the lattice, isn't it? So in Schottky defect, density of the overall compound decreases. Please make a note of it, right? In the previous case, that is a Schottky defect, right? Since one A plus and one B minus are completely moving out of the lattice, the mass is changing, right? The overall mass of the substance is changing. Thereby, density will get decreased, right? In Schottky defect, density decreases. That is a very main point, right? But here, in case of your Frenkel defect, nothing is moving out of the lattice, so you can see the density is constant. The density is not changing. Stoichiometry is also not changing. But in your Schottky defect, stoichiometry is not changing, right? But still the density is changing. Density is actually getting decreased in case of your Schottky defect, right? So please make a note of it, right? Okay, so that is about Schottky defect, and which and all can be examples, AGCL, AGI, right? All these things can be examples. Okay, Fine. So that's about the stoichiometric defects, people, right? And there is one tricky thing. When I go for AGBR, AGBR shows both Skotsky as well as frontal defects. Okay, AGBR. The AGBR will show Skotsky as well as frontal defects. This is the only compound, right? Other than that, for frontal defect, I have AGCL and AGBR, sorry, AGI, right? And I told you in case of your what is that, Skotsky defect, right? I gave the example of KCL and AGBR. AGBR can be an example for frontal defect also. Okay, fine. So that's about Skotsky defect. Moving on to the non-stoichiometric defects. That means the ratios are going to get affected. Okay. So in your non-stoichiometric defects, I told you I can have two types, right? Say first one is metal excess defect, right? I think from the name itself you can understand what I'm trying to say, right? So the stoichiometry requires some ratio, right, of the cations and anions. Metals again generally cations, right? So stoichiometry requires some constant ratio of the cation and anion, but the amount of cations are more than the required amounts, right? Are more than the required amounts. Okay, so now how will I, right? Now how will I be able to visualize it, right? So now metal excess, right? So I'll be able to visualize this in two ways. Okay, metal excess can be visualized in two ways. So the first way is that actually there is some metal extra, right? One extra cation is there. That is one way of saying. Or I can say that there can be lesser number of anions. By that, what is happening? If I have the number of anions to be less than what is required, definitely metals are in excess. Are you able to get what I'm saying? Right? So the first case is that actually there is extra metal. I'm adding extra metal. That is first case. Second case is that something is happening that some of the anions are lost. Now what will happen eventually? The metals will become in excess. Right? So we'll see both the cases what is going to happen. Right? So I will say metal excess due to addition of cations. That's the first point. That's the first case. Right? Okay, we'll see the second case later. So metal excess due to the actual addition of anion. So we'll see what happens. Right? So again, I have the lattice. So I have A plus, D minus, A plus, D minus, D minus, A plus, D minus, A plus, A plus, D minus, A plus, D minus. Okay. So I have my perfect lattice with me. Okay. So so now I have to, what is happening here? I am going to add cations, right? Now you can see that already all the lattice points are occupied, right? All the lattice points are already occupied. So if I'm going to add an extra cation, right? So definitely it has to go to the voids. It has to go to the empty spaces, isn't it? Say I can just mark it somewhere here. One second. Oh, okay. So due to actual addition, say I can mark 1 A plus here, extra, right? You can see it is A. Okay. So 1 A plus in the voids somewhere. Okay. Now please understand the stoichiometry is affected. No doubt about it. I have extra cations, no doubt about it. But please understand the overall charge of this entire molecule should be 0. That you have to make sure. Even though stoichiometry is getting affected, right? Even though stoichiometry is getting affected, the overall charge should be constant. Constant in the sense the overall should be neutral, isn't it? Now I have added an extra positive charge, right? I have added an extra positive charge. So what will the molecule do in order to maintain the charge balance is that you can see that obviously this A plus, how it would have been formed? It would have been formed by A losing an electron, isn't it? This A plus would have been formed by A losing an electron to form A plus, isn't it? So the charge balance here, that A plus, the cationic charge, is going to get balanced by the electron lost by the A, right? I'm going to have the cationic charge, the positive charge is going to get balanced, right, by the electron lost by A. Say you should have one more electron somewhere in the lattice. Again, all the lattice points are occupied. So you have to make sure somewhere in the voids, I have one electron also. So I'll put the electron here. Okay. So please understand what I said. The overall stoichiometry is affected, no doubt, because I have one extra cation. One A is extra, right? But that doesn't mean that you should have unbalanced charge also. You should have overall charge to be zero. So now you add an extra positive charge. It has to be, say, balanced with the help of an electron. So that electron also is going to be there at the voids. So this is what is called as your metal excess defect due to addition of cations. Okay, fine. Now next case, right? So that's about due to addition. So next case is due to a removal of anion. Due to removal of anion. Again, by this I make sure that the metal is in excess. Okay, so now what is going to happen? It's very simple. Okay, so I have A plus, B minus, A plus, B minus. I'll just only write two rows. B minus, A plus, B minus, A plus. Okay, right. So this is the perfect lattice, right? Now what I said, I am going to remove an anion, right? Say I remove any one of the anion. The anion is not there. Stoichiometry is affected, right? Now I have again more metal excess or cation excess, right? So now again I have to make sure that the charge balance is maintained, right? So obviously you cannot just put it empty in the lattice point, right? In the lattice point, I am going to have an electron. Okay. Now I'm going to give a special name to this site where the electron is there. This particular site is what is called as your F centers, right? This particular point where the electron is occupying is what is called as your F centers. Very important. Okay, so F centers will come into the picture only when I have metal excess defects. That too, when the metal excess defect is caused by the removal of an anion. Okay, right? So this F center is very important. The F center is the place where basically it should have been an empty lattice point because the anion is lost from there. But in that position, I have an electron to make sure that the overall charge is balanced. Overall charge is zero. Okay, so that's about metal excess defects. So lastly, when I go for metal deficiency, again, it's going to be exactly similar as metal excess. Metal deficiency defects. Right. So metal deficiency defects very easy. Right. So again, I can have two types. Right. I can have two types where first case can be removal of a cation. Obviously, removal of a cation makes sure that I have metal deficiency. Right. So it's going to be like this. Okay, I'll write only two of the things: A plus, B minus, A plus, B minus, say B minus, A plus, B minus, A plus. Okay, this is the perfect crystal, right? So now what I'm going to do is that I am going to remove one cation. Okay, now I still have my metal deficiency, right? But again, stoichiometry is lost. The ratio is not constant anymore, right? But I have to make sure that the charge is constant. That is, the overall charge is zero, right? So how are you gonna make sure? Here, can you just come up with your own ideas? How can I make sure that there is extra positive charge somewhere, somehow added? Can you come with an idea?
So one of the anions can lose its electron to become.
Okay, one of the anions, if they lose electron, I'll get negative charge. I already have excess negative charge. Because I have one cation lost, I already have extra negative charges. I have to nullify it. So what should I do? No, I don't expect you to know the exact reason, but I'm just checking whether you can come up with your own reasons, how creative you are. No idea. Okay, so I will tell you the answer. So people, right, this kind of deficiencies can be shown by metals with variable oxidation states. Right, this kind of defects can be shown by metals which can exist in more than one oxidation state. Right. So what is going to happen is, since I have one extra negative charge, so what is going to happen is one of the cations are not going to exist in +1 state. Instead of that, they will actually exist in +2 oxidation state. Right? They're going to exist in +2 oxidation state. Now what happened? I removed a cation, but I added one more extra positive charge also by making it 2+ and not 1+. Okay, so this exactly is what is called as your metal deficiency defect due to removal of a cation. Right, so when you remove the cation, one of the A plus will change its oxidation state to +2, making sure that the overall charge is 0. Okay, right, so this is what is happening. Next, the last one. One second. Okay. So the last one is due to addition of anion. Obviously, again, if I add anion, again, that will metal will become deficient. Now, non-metals will be in excess, right? So again, same thing. So A plus, B minus, A plus, B minus, B minus, A plus, B minus, A plus. Okay, right. So now what I'm going to do is that I'm telling you I'm going to add an anion. Okay, now please understand, this is theoretically not possible. This doesn't happen in reality. This is just a concept, but still people are scientists are trying to make sure that this kind of defect is also possible. But like, even if it happens, it is very, 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 very rare. Okay, because why? Because you can see that I'm going to add an anion. Okay, already all the lattice points are occupied. So the new anion has no place to go other than to occupy the voids. Right, other than to occupy the voids. Correct. Right. So, and obviously I know the anions are generally bigger. Right, anions are generally bigger. So obviously them occupying a void is a tough scenario. Right. So anyways, we will visualize it however it is. So I'm going to add an anion. So one of the anions are going to occupy the voids, the interstitial space. Okay, so now again, I have added an anion, I have added extra negative charges. So definitely your stoichiometry is lost, no doubt about it. But still, I have to make sure that the charge is also balanced, right? So again, what I did in last case, I made sure that one of the A plus becomes A2 plus. So here also I can make sure the same thing is happening. So I added extra negative charge. I add an extra positive charge by making one of the A to be A2 plus, right? So this is what is called as my metal deficiency due to addition of anion. Okay, so these are all the different types of defects you can have in solids. Okay, any questions? Any question from any of the 4 defects you want to ask me?
No, sir. It's clear.
Okay, hope everything is clear, right? That's it, guys. The chapter is over and my job is done. Like, they have allotted me physical chemistry, right? And I think I have done I have done what is to my heart is a very good, like, not very good job. I think at least I have not done anything against my conscience, right? So whatever has to be taught, whatever the problems has to be solved, all those things have been done in a very perfect way, right? So if you still have any problems, if you still have, sir, this chapter, this particular part, I'm feeling problematic, right? So you can tell the management, so we can see what we can do. Is that cool? And in very soon we'll be coming up with your revision plan, right? So we'll see what all chapters I take at that time, right? So I would prefer to take organic, right? Because physical, organic, inorganic. Organic is my favorite part, then physical, and the least is inorganic. Definitely the P block, D and F block part. So we'll see, right? So which chapters I take at that time, right? So guys, okay. So until then, bye
Thank
bye.
you, sir.
Thank you. Yeah,
Thank you, sir.
thank you.
Thank you,
Thank
sir.
you, sir.